Welcome to today's MedPhysio tutorial. Smooth muscle is everywhere, lining your blood vessels, moving food through your gut, and regulating airway tone. Unlike skeletal muscle, smooth muscle doesn't rely on fast, repeated contractions. Instead, it specializes in slow, sustained, energy-efficient force generation, which is crucial for maintaining tone and regulating flow. Today, we'll explore the beautiful mechanisms behind this remarkable tissue. Understand why smooth muscle is important. Consider a patient with severe asthma. The airway smooth muscle contracts excessively, narrowing the lumen. Or consider hypertension. The vascular smooth muscle tone is chronically elevated. Understanding the mechanism of contraction helps explain how drugs used in treating these conditions work. So, we'll begin by exploring the structural features of smooth muscle. From there, we move to the sources of calcium ion, the signal that wakes the cell. Once calcium levels rise, we follow them into the myosin light chain kinase pathway, the moment that turns a chemical signal into a mechanical force. Next, we'll examine the Latch-Bridge Mechanism, a remarkably efficient mechanism that explains how vessels can hold tone for hours without fatigue. After that, we shift to relaxation pathways, where the cell returns to its resting state. And finally, bring these ideas together by distinguishing phasic and tonic smooth muscle. At the end of this tutorial, I expect you to know how to draw and label a smooth muscle cell. Then we move into the signaling core, as the interaction between calcium, iron, and calmodulin. Understand how this partnership acts as the switch that activates the MLCK, setting myosin into a state where it can generate force. Let's build on this, be able to describe how the myosin light chains regulate contraction. Next, you learn why smooth muscle is slow but incredibly energy efficient. And finally, be able to apply these mechanisms to vascular and airway physiology. By the end of this tutorial, you will not only know the steps, but understand how they fit together and how they shape the behavior of the organs that rely on smooth muscle every moment. The smooth muscle looks simple, but can be a bit functionally complex. Inside, the layout is very different from the organized stripes of the skeletal muscle. There are no sarcomeres. Instead, the contractile filaments attach to dense bodies in the cytoplasm. These function as flexible anchor points, allowing the entire cell to shorten in a twisting three-dimensional manner. This arrangement is the structural signature of smooth muscle and explains its ability to maintain tone across long stretches. Now, zooming in further, you'll see the actin and the myosin filament. Now, the ratio of actin to myosin is high, and this abundance of actin contributes to slow, sustained contractions rather than the fast, powerful ones seen in the smooth muscle. Along the membrane, instead of the deep T tubules seen in skeletal muscle, the smooth muscle uses small invaginations called caveolae. These bring extracellular calcium close to the contractile machinery, enabling the cell to respond efficiently to signals without an extensive tubular system. And finally, the cells are connected by gap junctions. These allow ions to pass directly from one cell to the next. These electrical coupling lets whole sheets of muscle contract as a coordinated unit, producing rhythmic waves of activity. Together, these features form the structural foundation that gives smooth muscle a slow and steady behavior. Like skeletal muscle, which relies primarily on its sarcoplasmic reticulum for calcium. Smooth muscle depends heavily on extracellular calcium entering through the cell membrane. There are four main calcium sources. One, the voltage-gated calcium channels. These warrant or grant only extracellular entry. Now, when smooth muscle membrane depolarizes or when triggered by neurotransmitters, pacemaker activity, or mechanical changes, voltage-gated channels, calcium channels open. This allows calcium ions from outside the cell to flow into the cell. There are two types of calcium channels. Here we have the L type calcium channels. This open during significant depolarization, providing and provide sustained calcium influx. Second is the T type. This opens briefly during mild depolarization and contribute to early calcium influx. L type, T type, voltage gated channel. Now, these extracellular influx is typically the largest contributor to the rise in intracellular calcium during contraction. Very important. The second source is through the ligand-gated pathway or the receptor-activated pathways. When signaling molecules like norepinephrine bind to cell surface receptors, they trigger a cascade. I'll explain this. Norepinephrine binds to the coupled receptor, like the GK coupled receptor. This activates phospholipase C. Phospholipase C is a membrane enzyme that cleaves phospholipids. Now, phospholipase C generates inositol triphosphate, which is a signaling molecule and second messenger that releases calcium from the endoplasmic reticulum. IP3 binds to IP3 receptors on the sarcoplasmic reticulum, right? The stored calcium is then released into the cytoplasm. See, to the cytoplasm. So, first, voltage-gated calcium channels. Second, ligand-gated pathways, receptor-activated pathways. Additionally, this pathway opens the transient receptor potential. See that here, TRP channels, allowing more extracellular calcium to enter. Think of the internal sarcoplasmic reticulum release as a quick boost, not the primary source. It supplements the larger extracellular influx seen earlier. Right? Very good. Now, the third source is the stretch activated channels. And the smooth muscle cells are physically stretched, such as in a filling bladder or a pressurized blood vessel. Stretch activated channels open mechanically. These provide a direct link between physical distension and contraction, allowing extracellular calcium to flow in without the need for electrical or chemical signals. 1, 2, 3 mechanisms. Finally, there's the store operated calcium entry. This is a kind of refilling mechanism. When the sarcoplasmic reticulum's stores become depleted, the cell activates the store operated calcium entry. This mechanism brings in additional extracellular calcium to refill the sarcoplasmic reticulum stores, and it brings about sustained and prolonged contractile activity. Now, how all of this come together? When all of these channels open and allow calcium ion to enter, that's positive ions the cell membrane becomes depolarized. The depolarization leads to opening of more voltage-gated uh, calcium ions, calcium channels, allowing more positivity. This creates a kind of positive feedback loop that amplifies calcium entry. So it's all about the entrance of calcium ions, positivity, and depolarization of the cell membrane. So now let's discuss the mechanism of smooth muscle contraction. Remember I said earlier that there are different sources of extra or the calcium required for the process. It's about the extracellular influx and from the sarcoplasmic reticulum. Now, when unlike the skeletal muscle where the calcium interacts directly with troponin, smooth muscle uses calmodulin, and it uses it as a sensing molecule. Now, when calcium binds to calmodulin, it forms a complex that's very powerful regulatory complex. That's the calcium calmodulin complex. Now, once it forms, it regulates myosin light chain kinase. Is an enzyme that decides whether myosin is in a state that can generate force. And activated MLCK then phosphorylates the myosin light chain. Is active, phosphorylates the myosin light chain. This single phosphate group is what flips myosin into its active high affinity state. This is where your exam tip becomes very crucial. It's the phosphorylation of the myosin light chain is the rate limiting step of smooth muscle contraction. Examiners love to see this phrase because it captures the central regulatory point of the entire mechanism of smooth muscle contraction. Now, once myosin is phosphorylated, its ATPase activity turns on, allowing it to hydrolyze ATP, undergo the conformational changes needed for coke. So once it's active, a lot of things happen. We'll discuss that later on. But to summarize, um, there's a cross bridge cycling begins, attachment, the power stroke, detachment, and reattachment, generating force that can be maintained for long periods. So this slide holds the essential sequence of smooth muscle contraction. Calcium binds to calmodulin, MLCK is activated. Once activated, myosin is phosphorylated, and once it's phosphorylated, the ATPase activity increases, cross-bridge cycle begins, and you have contraction. Now, if you can visualize these chain that we just described smoothly, the rest of smooth muscle physiology snaps cleanly into. After the initial contraction has begun, myosin has been phosphorylated, something unusual happens. Some myosin heads remain attached to the actin even as their phosphorylation level falls and ATP availability drops. Instead of cycling rapidly, they settle into a slower, almost resting grip. This is the latch state. Because these attached bridges turn over very slowly, the cell can maintain force with remarkably little ATP consumption. There's no frantic cycling, no heavy energy demand, just a quiet, sustained hold. And it's this mechanism that forms the physical basis of tonic contraction, especially in blood vessels, sphincters, and other structures that need to maintain steady tone for long periods without fatigue. So remember when you're writing an exam, always use the phrase, it's an energy efficient tonic maintenance. Next comes the relaxation of the smooth muscle after contraction. Let's discuss the relaxation pathway. The first change is the removal of calcium ions from the cytosol. Pumps begin working steadily. The sarcoplasmic and the sarcoendoplasmic reticulum calcium ATPase draws calcium back into the sarcoplasmic reticulum. The plasma membrane calcium ATPase draws calcium, transports it across the membrane, and the sodium calcium exchanger assists by swapping intracellular calcium for extracellular sodium. So, as the calcium levels fall, the cell's permission for contraction gradually fades. Now, with less calcium available, the calcium calmodulin complex fades, gradually fades away, right? And it disappears. All you have left is calmodulin neurocomplexes. And as this happens, the myosin light chain kinase falls silent. This hands control over to myosin light um, chain phosphatase, which slowly dephosphorylates myosin. And without the phosphate group, myosin loses its ability to sustain cross-bridge cycling. As phosphorylation drops, cross-bridge activity gradually decreases, allowing the muscle to relax smoothly rather than snap back suddenly. This slow transition is why smooth muscle can shift between contraction and relaxation without producing. Smooth muscle operates in two main patterns, phasic and tonic. Phasic smooth muscle produces quick, rhythmic contractions, ideal for the guts and bladder, where repeated bursts driven by rapid calcium ion changes allow fast cycles of contraction and relaxation. Tonic smooth muscle maintains sustained tension with low energy use, as seen in blood vessels and sphincters, shows higher calcium ion sensitivity, and relies heavily on the latch state, enabling long-lasting with minimal ATP consumption. Though both types use the same contractile machinery, they differ in calcium ion handling, myosin phosphorylation, dephosphorylation rates, and ease of entering the Latch-Bridge mechanism. In simple terms, phasic equals rapid rhythmic bursts, tonic equals steady energy efficient maintenance, a useful way to classify smooth muscle function across organs. As we proceed to this slide, consider it a guide for crafting a high quality exam answer. Always begin with a definition, one short line that frames the entire mechanism. It signals to the examiner that you understand the essence of smooth muscle contraction before diving into details. From there, you offer a brief outline of the structural features, just a sentence or two about the spindle shaped cell, the absence of sarcomeres, and the role of dense bodies. This anchors your mechanism in the architecture that makes it possible. Then you describe the excitation leading to calcium entry. Next comes the core pathway, calcium binding to calmodulin, activation of MLCK, and the phosphorylation of myosin, leading to cross-bridge formation. After establishing contraction, you mentioned the Latch-Bridge mechanism and relaxation. These two ideas show that you understand smooth muscle not just in the moment of activation, but in its energy efficiency and its ability to return to rest. And finally, you close by adding clinical correlations. A single line about vascular tone, airway narrowing, or pharmacological modulation is good enough. This slide gives you a simple flow: definition, structure, calcium entry, MLCK pathway, latch and relaxation clinic, and then clinical links. When you follow this structure, your answer becomes organized, confident, and examiner friendly. As we come to this final slide, let's gather the key ideas into one quiet, coherent picture. Smooth muscle contraction is driven by calcium-dependent, myosin-linked regulation. The rise in intracellular calcium binds to calmodulin, activating MLCK, which phosphorylates the myosin light chain and initiates contraction. Relaxation begins when MLCP desphosphorylates myosin, a simple balance between MLCK and MLCP, acting as opposing controls. The muscle's exceptional energy efficiency comes from the Latch-Bridge Mechanism, which maintains force with very little ATP. This allows smooth muscle to sustain long-lasting graded tension. These same molecular processes support two major functional patterns: physical activity, where there's quick rhythmic contractions, for example in the gut, and tonic activity, which are prolonged tone and seen in blood vessels and sphincters. So in summary, you have calcium ion, calmodulin, MLCK vs MLCP, latch bridges, phasic vs tonic behavior, and this shows the core logic of smooth muscle contraction in just one sequence. Here are some quick takeaways. Let's gently distill the core ideas that run through smooth muscle physiology, the concepts that hold the entire topic together and will serve you well in any exam question. First, remember that smooth muscle contraction is slow, sustained, and energy efficient. Its purpose isn't rapid movement, but controlled, graded force that can last for long periods. This behavior makes perfect sense once you recognize that regulation occurs at the level of myosin phosphorylation, not at actin, since skeletal muscle. Next, recall that calcium can come from the extracellular space or from the sarcoplasmic reticulum. This dual sourcing is one of smooth muscle's key adaptive features, and in many tissues, extracellular entry is the dominant contributor. The latch mechanism allows smooth muscle to maintain tone while consuming little ATP. Quiet, economical strategy built around slow cycling cross bridges that hold force without fatigue. And balancing all of this is the nitric oxide GMP pathway, which promotes relaxation by enhancing MLCP activity. It's the system's built-in brake, allowing tone to be released gently and close. A quick self-check. What enzyme phosphorylates myosin light chain? Name one tonic and one phasic smooth muscle example. Where does calcium often come from? What activates MLCP? Which mechanism explains long-lasting tone with minimal energy use? If these answers come easily, you've captured the heart of it. Thanks for learning with MedPhysio. The goal is simple: to make physiology clear, connected, and intuitive so that every new concept feels like a natural extension of the last. I'll see you in the next MedPhysio session.